Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the Electrical Engineering channel. In this lecture, I will solve a couple of examples which are related to the swing equation in power system operation and control course. In the first example, we have a 4-pole 50 Hz 11 kilovolt turbo generator which is rated at 75 megawatt and 0.86 power factor lagging. The rotor has a moment of inertia of 9,000 kilogram meter square. Find the inertia constant H in megajoules per MVA and M, which is angular momentum, in megajoule second divided by electrical degrees. So let's solve this example, and first we will evaluate the angular frequency or angular velocity, which is equal to 2 pi f, and that will be equal to 100 pi radian per second. Now kinetic energy is equal to half j omega square or I omega square. I is the moment of inertia, so that will be equal to 443.682. The MVA rating is equal to megawatt divided by power factor, and that will be equal to 87.2093 MVA. And H factor or inertia constant is equal to megajoule divided by MVA. So the ratio is equal to 8.0875. And the angular momentum is equal to MVA H divided by 180F. So MVA is also called S machine. S machine into H divided by 180F, and that will be equal to 0.049. Since we are asked to evaluate angular momentum in these units and we have electrical degrees over here, so that's why we have to use this angle in degrees. If we had radian over here, electrical radian, then we would have used pi over here. So this is our final answer of the angular momentum. So let's solve another example which is also very simple, and in this example we are given two generators rated at 4 pole 50 Hz 50 megawatt 0.85 power factor lagging with moment of inertia of 28,000 kilometers square kilogram meter square, and two pole second machine is 2 pole 50 Hz 75 megawatt 0.82 power factor lagging with moment of inertia of 15,000 are connected by a transmission line. Find the inertia constant of each machine and the inertia constant of single equivalent machine connected to infinite bus. Take 100 MVA base. So kinetic energy for the first machine is equal to half I omega square, and it is equal to 1380.34 megajoule. MVA is equal to megawatt divided by power factor, and it is equal to 58.82. So H1 will be equal to this value, which is equal to the ratio of kinetic energy and MVA rating, and M1 is equal to this value, right? And here we have MVA divided by pi f, so that is equal to 0.1534 megajoule second divided by degrees. For the second machine, we can do the same operation, and the kinetic energy is equal to this. This is MVA rating, this is H2, which is inertia constant. Now the two generators are connected in parallel with the same transmission line. So for the parallel connected machines, the angular momentum will be evaluated using this expression. So the reciprocals of the angular momentum will be added. So M is equal to M1 M2 divided by M1 M2. So this is the same way we evaluate the equivalent resistance or equivalent impedance of parallelly connected components. So M will be equal to 0.0535 megajoule second per degrees, and GH is equal to 180 into 50 into M, which is equal to 481.5 megajoules. So that is all about our today's lecture, and I will recommend you to solve these examples from the textbook of Power System Analysis by Murthy. Okay, so if you solve these examples, that will be much beneficial for you. And for watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.